Welcome back to Chemistry with Miss B, and today we are going to be going over the May, July, June, or whatever you want to call it, 2021 past paper. You would have done this exam on Wednesday, so proceed with caution. Alright, so the first question: a student conducted an experiment to determine the products formed from the electrolysis of aqueous copper to sulfate using inert electrodes. Figure 1 shows a simplified diagram of the apparatus used. The procedure is that a current was passed through the electrolyte and the starting time was recorded. At 10-minute intervals for 1 hour, the volume of oxygen gas evolved and the mass of copper deposited is measured. At the end of the reaction, the total mass of copper deposited was 4.85 grams. The volume of oxygen gas evolved is shown in the table 1 below. Alright, so it says define the term electrolysis. So this is the chemical change occurring when an electric current passes through an electrolyte. That's one. You can say it's the decomposition of an electrolyte when a current is passed through it. So there are many different ways you could define the term electrolysis. So once you say that current is being passed through an electrolyte and some type of change is happening, you're good to go. Then it says suggest one material that could be used as an inert electrode in the electrolysis of copper to sulfate, and that would be graphite electrodes. Then using the data in table 1, plot a graph of volume of oxygen measured versus time using the axis in figure 2 on page 7. So this is draw a line of best fit. Okay. So all you had to do was they gave you the calibrated axes. That was nice. That was really nice of them. And all you had to do was plot. So it would have been easy to plot on your x-axis because it was at increments of multiples of 10. That's an easy plot right there. That were exactly on 10, 20, 30, 40, 50, 60, right? So that was good. The only thing that was different would have been the y-axis where they had 10 spaces per increment, which was a single increment. So in between if you want to ever find out what each point is equal to, you simply do a subtraction of the lower number from the bigger number. So you do something like this. So say you pick 3 and 4. The increments are the same, 0, 1, 1, 2. You just add in 1 as you go up. So you would say, okay, let's pick 4 and 3. 4 minus 3 over 5, 10. So it's 5 spaces between the two big spaces, right? So that's 10. So 5 and then 10. So divide by 10. So you end up with 1 over 10. So each point would be 0.1. So then therefore, this would be 3.1, 3.2, right up 3.5, and then we have 3.9. So each is 3. You add 0.1 every time, right? Okay, so now that you know that plotting would have been very easy because it's all 2 decimal places, and the second decimal place here is a 0 for all of them. So easy. So on 10, it would be in 2.4, which is just under the 2.5 line. As you can see, after you plot all these points, you end up with a straight line graph. Then this is find the best fit line. So my best fit line is the one in purple. Okay. Then they said use the graph to determine the time it took for 5.5 cubic centimeters of oxygen gas to be liberated. So you just go from the 5.5 Mach. That says that's the amount of oxygen, so it tells you that. Bring it across and down. No, never mind, mine is a little off because I couldn't get it formatted based on the computer, but it should be running straight on this 5.5 line and straight down. And based on how it should be down, you should have gotten about 36, 37 minutes, right? So the ask to determine the time, so 36, 37 minutes around there would have been good because this is 35 Mach. And again, to work these out, to know these, again, you just minus the smaller number from the bigger number and divide by the spaces, and in this case end up with 10 over 10. So each space is 1, so it'll be 11, 12, 13, 14, 15, 16, 17. Right, so that was simple. Alright, so that was good. Now it says to identify all the ions present in the electrolyte used in the experiment. So I took the picture and pasted it here so we don't have to go back. And first of all, we need to note that it's an aqueous solution of copper sulfate. So if it's an aqueous solution of copper sulfate, then therefore there's water in here. So I wrote the ions that will come from the water, which would be hydrogen ions and hydroxide ions. And then I wrote the ions that will come from the copper sulfate, which would be the copper ions and the sulfate ions. Then they ask P and Q are electrodes shown in the apparatus used for the electrolysis of figure 1 on page 5. State which electrode is the anode and which is the cathode. Well, just look at which electrode is attached to which side of the terminal of the battery. So P is attached to the positive terminal of the battery and Q is attached to the negative terminal. So just remember the mnemonic panic. Positive is anode, negative is cathode. And so since this is attached to the positive side, this is the anode, and Q will be the cathode. Say one ion in the electrolyte that will drift towards the anode. Well, the ion that is most preferred would drift there first to the cathode, and we know that to the anode, sorry, and we know that ions that go to the anode are anions, and so we look at the anion reactivity series. Fiona's sun never comes by in October, so we look to see which one is on the lowest. It's the hydroxide anion, and that is lower than the sulfate anion, so therefore the hydroxide anion will come out first. Then they ask us to write an ionic equation for the reaction taking place at the cathode. So remember, at the cathode, we're going to have copper ions coming out of solution to become copper atoms. So to remember this, you would have your Cu2 plus, and what would happen is that you would gain 2 electrons. So basically, the copper ions become reduced. As you can see, it goes from a 2 plus state to a 0 state, and we go from being in an aqueous state to being solidified. And this would be your equation right here. Then there's a calculate the quantity of electricity that passed through the copper to sulfate solution when 3.5 amps of current flowed for 1 hour. Okay, so they gave us the amps, which is current, and they gave us the formula to work out charge. So we have quantity of electricity is equal to current times time. So therefore Q is equal to IT. We have I and we also have T, but we have to remember to convert T into seconds. So they gave us the unit of 1 hour, of an hour. So you have to convert from hour to minute to seconds. So you say if 1 hour is equivalent to 60 minutes and 1 minute is equivalent to 60 seconds, we could now correlate the minutes to seconds by saying 60 minutes, then 60 minutes is equal to X. You cross multiply and you end up with 3600 seconds. Now they went on to ask you to calculate the number of moles of copper deposited. So what you want to do is remember that 1 mole of any substance would have 96,500 coulombs times the number of electrons. We require that. So the number of moles will be equal to the amount of charge. Okay, so I times T. And so you could also relate it based on mass. Here you just change out these sides to mass, molar mass, and then mass. And so what I did is use moles simply because they asked for moles. So I would say 1 mole is equivalent to 96,500 times the 2 electrons that we saw earlier over here. The 2 electrons, which was in part C4. And then you multiply that and you correlate it to find the moles. So well, then therefore, well, X would require this amount, 12,600 coulombs, which is what we worked out earlier. See, we worked it out earlier. So they helped you, they let you work step by step, and once you knew that, you would have been able to find the amount of moles of copper. Okay, then now that you have the amount of moles, they ask you to calculate the mass of copper that was deposited. So what was the mass of the moles that you had? So given that the atomic mass of copper is 64, you say, well, 1 mole of copper is equal to 64 grams per mole, so therefore 0.065 moles of copper would have less weight, because if 1 mole has 64 and this is less than 1 mole, it would have less mass, and so you multiply these two numbers, as you can see, and you end up with 4.12 grams. This is to suggest one reason for the difference in the mass of copper calculated in D3 and the mass measured by the student, which is 4.85. Easy. So you just say the scale used may have had pre-existing faults leading to the collection of inaccurate data. Or you could have said the scale was incorrectly calibrated. Right? So things like that. Okay, so it says state the color change that would have taken place in the electrolyte after a few hours. Well, the electrolyte would have been blue in color because of the transition metal copper being in there, and it would have been in aqueous solution, so it would have been in ion form, so it would contribute to the color. And so once it passed the electricity through it, it would cause the copper to basically go from being in ions form to become atoms. So it would cause it to come out of solution and become solidified, solid. To, you know, we have atoms, these are atoms of it. And so the color will go from blue to colorless. Okay. Now the student was asked to use the same electrolyte to purify a piece of impure copper. State how the electrodes in figure 1 on page 5 can be modified to obtain pure copper from impure copper. Well, what you could do is make the anode impure copper electrode, and you can make the cathode a pure copper electrode. Okay. Alright, so we're on question 2. It says acids react with metals and bases to form salts. John conducted experiments to investigate the properties and reaction of acids using sulfuric acid, iron, and sodium bicarbonate. Define each of the following terms. So let's define acids. So acids contain a higher concentration of hydrogen ions. The more hydrogen ions it contains, the more concentrated it is. A strong acid protonates fully in aqueous solution, while a weak acid only does so partially. A salt is a chemical compound consisting of cations and anions bound together in a crystal lattice via ionic bonds, and the product is electrically neutral. Now, John dissolved sodium bicarbonate in water and tested the solution with red and blue litmus paper. The red litmus paper turned blue, however, the blue litmus paper did not change color. State one reason why the red litmus paper turned blue, but the blue litmus paper did not change. Well, if you remember, litmus paper is used to test whether something is acidic or basic. Okay, litmus paper and litmus solution. And once red litmus paper turns blue, that means that the solution is basic. And if the blue litmus paper does not change in solution, then therefore it's a basic solution. Okay? Now state whether the pH of sodium bicarbonate will fall within the ranges of pH is greater than 7. Yes, it will, because the pH that is greater than 7 is all basic, indicating something that is basic. So from 8 to 14 would indicate basicity. Well, from 1 to 6 will indicate acidity. In two separate experiments, iron metal and sodium bicarbonate were both treated with excess sulfuric acid. The results of both experiments are recorded in table 2 below. And here we have table 2, and it says by stating the two inferences that can be made from the observations in experiment 1, we need to complete them. So complete table 2 by stating the two inferences that can be made from the observations in experiment 1. So they said the solution turned green when the acid was added to the metal ion. Well, if it turned green, that means there's a presence of Fe2 plus ions. And I would think that for this, they want an equation, and the equation will show the ion in its neutral state becoming oxidized to Fe2 plus. And so with the colorless gas evolved, now a colorless gas evolved, and the splint goes off with a squeaky pop. That's a test for hydrogen gas. Right, so then therefore hydrogen gas was given off in the reaction between iron and the acid. And so we will write a half equation for that, where we have 2 hydrogen ions, and then you have 2 electrons to produce the hydrogen gas. And that was it for that. Now it says state 2 physical properties of iron metals, and I put 4, but you could be lustrous, sonorous, ductile, malleable. You could even write that would be, I guess shiny would fall under lustrous, and you could even write that it was gray in color. Yeah, so anything that you could observe with your eyes. So write a chemical equation for the reaction that occurs between iron, metal, and sulfuric acid. So you just have to remember that when a metal reacts with an acid, you always get a salt plus hydrogen gas, which is what we have here. So when the metal was reacted mixed with the sulfuric acid, we ended with the salt, iron sulfate, and the gas, hydrogen gas. Now it says describe a test that can be used to confirm the identity of carbon dioxide in experiment 2. Include your expected observations. So the test would be to bubble the gas through lime water, which is known as calcium hydroxide, and you would observe that it would turn cloudy due to the formation of the white precipitate calcium carbonate. Upon extended bubbling, the white precipitate will be dissolved and to form calcium hydrogen carbonate. Okay, so you could have put all of that, or you could have stopped at a white precipitate would form, because it's 2 marks. So I guess 1 mark for this and 1 mark was for this. Then we have write a balanced equation including state symbols for the reaction between sodium bicarbonate and sulfuric acid. So sodium bicarbonate is NaHCO3 plus H2O. You will get a salt, and anything that has a carbonate in it, you will get carbon dioxide and water, and all you had to do was balance. So I always tell people balance by writing your atoms for each side. So we have sodium atoms here, we have hydrogen atoms, we have calcium, we have carbon atoms, we have oxygen atoms, and then we have this sulfate anion that goes through unchanged. So I wouldn't even bother about that. Iron, I wouldn't bother to break it up since it goes unchanged. So that's one less headache. And I will write the same atoms over here and balance. So I have here, I balanced it already, but I'm just showing you that this is the easy way to do it. So the 2 in front here would account for all atoms involved, all species involved. So since we have 2 in front here, it will be 2 sodium atoms. And then we have hydrogen, so it will be 2 hydrogen atoms from this substance. and then we have 2 here from the sulfuric acid that will add up to be 4. And then with carbon, we have 2 carbon atoms, no more anywhere else. We have a 2 here. And then with oxygen, we're only looking at the oxygen in the carbonate because the carbonate is the one it broke down. You know, we don't have carbonate over here, we have carbon dioxide. So we have 6 oxygen atoms. And of course we have 1 polyatomic anion of sulfate, so that's 1. Okay, and now over here we're going to see if we have the same numerical code coming down. That's why I put them in order. And if you look at it, you see I have 2 atoms of sodium. And with hydrogen, we go over here, we have 4. So 2 times 2 is 4. Now with carbon, we see we have 2. And with oxygen, again, ignore this polyatomic anion because it goes through unchanged. It just swapped partners. We're looking at just the hydrogen, the oxygen atoms over here in carbon dioxide and water. So we have 4 here. That's 2 times 2 is 4. And remember, this 2 only accounts for this atom, which is oxygen. And then we have 2. So 4 plus 2 is 6. And then we have 1 sulfate anion. The code is the same, 24261, 24261. So we know we are balanced. So I just put that in. So if you don't know how to balance, that is the way to balance. Okay, so we're on to question 3. 2 organic compounds A and B have the following molecular formula. Compound A is C3H8 and compound B is C4H8. Write the general formula for the homologous series to which compound A belongs. So it's an alkane. So the general formula for alkane is CnH2n plus 2. So we see it makes sense because if we said 3 times 2, it'll be 6. Then we just add 2 to make it 8. Okay, so that makes sense. Then it says list 3 general characteristics of homologous series other than the general formula. The polarity, the reactivity, and they have the same functional groups, right? Now identify the homologous series to which compound B belongs. Well, since the number of hydrogens can be divided by the number of carbons without any remainders, we know that it's an alkene, right? So from there on, we had to draw in the spaces provided a fully displayed structural formula for compound A and B, and there they are. Compound A being the alkene and compound B being the alkene. Okay, so compound A is propane while compound B is butene. And always make sure to count back to make sure your numbers match. So with compound A should be 3 carbons, 1, 2, 3, and 8 hydrogens. We have 3 here, 3 is 6, 7, 8. And with compound B we have 4 carbons, 8 hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8. So you always count back. Okay, and especially with double bonds here, you realize there's only 1 hydrogen necessary for this carbon since carbon bonds 4 times. 1, 2, 3, 4. Okay. Now a sample of compound A was placed in test tube 1. A sample of compound B was placed in test tube 2, and 1 centimeter cube of acidified permanganate solution was placed in each test tube. State what would be observed in each test tube. So in test tube 1, there'll be no reaction simply because it's an alkane. Alkanes are saturated. Alright, they hardly react, and if they do, it's under extreme conditions or with a catalyst. With acidified potassium manganate solution, for the alkene, it would turn from purple to colorless and you get an antiseptic scent given off. Now, it's an oxidation reaction. Right, so in the presence of the acidified permanganate solution, the alkene will be converted to a diol. Okay, that's the reaction. So check out my flashcard section on reactions and you would see it right there. Then it says give one use of each of the following compounds. Compound A is a fuel. It is, what was compound A again? Compound A is propane. It's a fuel. And compound B is seen as an alkene. It can be used as a raw material for making plastics. And that's the end of question 3. Now going on to question 4, we have, well, this is section B. The modern periodic table is arranged such that chemical elements are grouped according to the chemical properties they exhibit. Many of the elements in the periodic table exist as a mixture of the isotopes. Yeah, we know that. And so the table 3 shows the symbols of selected elements in the periodic table. Okay, so then it says state the electronic configuration of silicon, justify its placement in period 3 of the periodic table. Okay, so this is how the periodic table looks, and we know that this is 1. So remember the elements in the periodic table are placed in the order of the number of protons. The atomic number is the number of protons. So they're also neutral. So the number of protons will be equal to the number of electrons. So once you count them out, you'll be able to realize that, okay, I know the number of electrons, definitely. So if this is 1, then this is 2. And you go from left to right. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we know that silicon is the 14th element on the periodic table, and therefore, since it's neutral, it would have 14 protons, and the number of protons would be equal to the number of electrons, hence it would have 14 electrons. The first energy level can hold a maximum of 2, second energy level a maximum of 8, and then the remainder. So how I do this, I would usually write out the amount of electrons I'm dealing with, and I start to subtract. So this will be my first energy level. So we know that 2 would come out of this set. So we're ending up with 12 electrons. And in our second energy level, we need 8 electrons to fulfill the octet. So since we have more than 8, we know 8 will be leaving, and we'll be left with 4 electrons. Now the next energy level can hold a maximum of 8, so therefore all 4 of these electrons will occupy the third energy level. And so when you write out the electronic configuration, you write 2, 8, 4. And since it's 3 numbers, we know it's in period 3, because the electrons occupy 3 energy levels. Okay, so first, second, third are 3 orbitals. Then they said in the space below, draw a dot and cross diagram to show the structure of the covalent bonding present in a fluorine molecule. If we go back here, we would see that fluorine is the 9th element. So therefore we would have 9 electrons. Again, this is when fluorine is as a neutral element. And so since it would have 9, we have to write out the valence, we have to write out the electronic configuration. And we see here that the first, if we have 9 electrons, we know the first energy level can hold 2. And then we left back with 7. So the second energy level can hold a maximum of 8 electrons. So therefore it would be 2, 7. Or you could have done it such that you look at the grouping. So we see that this is group 1, group 2, 3, 4, 5, 6, 7. So since fluorine is in group 7, it would have 7 valence electrons. So that means you could do it this way, where you work out the electronic configuration, or look at which group fluorine is in, because the groups tell us the amount of electrons that are available for bonding, which is known as valence electrons. So that would be 7, and since we're dealing with bonding, we only need to deal with the valence electrons. This is like a Lewis dot structure. And so one of the fluorines would have dots, So 7 dots representing 7 valence electrons, and the other one in place of dots will be x's to show the difference, and the covalent bond will be the 2. The x and the dot together would form a single bond between them. 2 electrons is equivalent to 1 bond. Okay, so that is how you should have drawn this. 2 marks. Now, it says define the term isotope. The species with the same number of protons but different numbers of neutrons. And if you had no idea what, if you didn't remember, because if you didn't have an idea, you wouldn't know. But if you didn't remember what isotopes were, this question should have, sent signals to your satellite dish, which is your brain, and you would have said, oh, this looks familiar. And you come down here because it says the element C has isotopes. So from the list of atoms of C below, identify those that are isotopes. Now, this could be interpreted in many ways, and I mean, I interpreted it in 2 ways. But to cover my hide, if I was a student, I would just do it as is, because it sounds as if they wanted to just list a set, and not, because I would use the word group the atoms according to the isotopes that there are, instead of list atoms, because I mean, if you say group, then I'm going to have an idea that you're saying, okay, a set of them go together, another set go together. Anyway, I digress. So I will group these 2 as isotopes because they have the same amount of protons and different mass numbers. So these go together. Like as I said, so they have the same amount of protons but different neutrons. And if you have different neutrons, that means your mass number is going to be different. And so C7 and C7, 14 and 12, these go together because the proton count is the same but the neutron count is different. So I grouped. Now they say give 2 examples of radioisotopes and state 1 use of each. So you are expected to know some radioisotopes and their uses, and one of them is cobalt-60, which is used in radioactivity or in radiotherapy in the treatment of cancer. And uranium-235 is used in nuclear plants to produce clean, cheap energy. Okay, so magnesium and calcium both react with water. Okay, and we could see that they're in group 2. So what I did is copied the picture from the next page so we wouldn't have to be going back and forth. And it said to write a chemical equation including the state symbols for the reaction of calcium in water. So you have a metal, a reactive metal being placed in water. It's exothermic. You have some heat coming off and it's going to form a base. Right, so you can form a base. Alkaline earth metals form bases and then give off hydrogen gas. Okay, so this again is balanced. We have 1 calcium atom, we have 4 hydrogen atoms, so 2, so this accounts for the hydrogen, and 2 here, 4, and then we have 2 oxygen atoms. So yeah, good. So an unknown element X is shown in table 3 on page 15. So like I said, we don't want to go back. And it says predict the order of reactivity of X, magnesium and calcium in water. Well, this one, we know magnesium is really reactive in water. And if you didn't know how to answer this question, you could even write up your reactivity series. Remember, please send Charlie's monkeys and zebras in large, high cages more securely guarded. So this is the reactivity series for the cations, right? All of them are metals except for hydrogen, and then you have carbon, which is between aluminum and zinc. But we don't really include that until we reach to things like extraction of metals from ores. That's when we come to it. And also electrolysis, But it's not really a popular We don't usually put it in there. Anyway, getting back to the case. So when you look at it, potassium is the most reactive and gold is the least reactive. Gold doesn't even react with acid. So most reactive, so when we come down, we have sodium, so then we have calcium. And as you can see, calcium is the second one underneath magnesium. So calcium is more reactive than magnesium according to the reactivity series that we have. So if calcium is more reactive than magnesium, then X should be more reactive than calcium, because we get more reactive as we go down. And that's basically based on the fact that you have the addition of more protons and the addition of more electrons. Actually, we have the addition of more electrons as we go down, and so with that we have electron repulsion acting, being a strong force, a strong, let's say, a reason why reactivity is so high is because of the presence of more electrons. Whereas magnesium has 12 electrons, calcium has 20. So for magnesium, the electronic configuration will be 2, 8, 2. And for calcium, the electronic configuration will be 2, 8, 8. That's 16, 17, 18, 19, 20. So imagine you have all these electrons. You have 16, 17, 18, 18 electrons with an electronic, they're repelling these two electrons, and you have just 10. So the greater the amount of electrons, the greater the repulsion these two electrons in the outermost shell will feel. So therefore, that makes calcium even more reactive than magnesium. And as you go down, as I tell you, it's more electrons being added, more electrons every time, right? So X will be most reactive, while magnesium will be the least reactive, and then we have calcium in the middle. Okay, so number 5, in many Caribbean countries, hydrocarbons are used as a source of energy. State 2 natural sources of hydrocarbons. So to remember this, you could say corn. There are many ways. So corn, coal, oil, natural gas. This is the one that is easiest for me: coal, oil, natural gas. So either of those would work. Then there's a fractional distillation of long chain hydrocarbons produces several fractions with varying numbers of carbon atoms. 3 of these fractions are shown in table 4. So state the name of any 2 fractions of the long chain hydrocarbons. So they have between 1 and 4 carbon atoms. No, the fraction 1 and 2 are easy because we learn how to read long chain hydrocarbons up until, let's say, 10 carbons or even 12. Yeah, 12 because dodecane. Anyway, some of us just learn up to 8. So this was fine. So we have butane here, octane. And then 20 to 40 might have been a little problem. But I said go with I would have put right here, like bitumen. Because that's the first level that they start heating up, and then in the fractional column you would see it as it go up. Right? It's in your book. I should have made a printout here. Yeah, I should have put something here. But you have the fractional distillation on the industrial level, where you have your thing like this, and you have it being heated up, and then you have the fractions coming off, going up, like a lot of fractions, and the latest fractions come off at the top. Okay, so check your text for that. Now we say Figure 3 illustrates the process of converting long chain hydrocarbons obtained from the fractional distillation into shorter chain hydrocarbons in the absence of a catalyst. That's very important that they write in the absence of a catalyst. So there's no catalyst causing this change. So it says state the name of the process illustrated in figure 3. Alright, so I mean, this is cracking. Once you go from long chain to shorter chains, you've cracked it. And usually when that happens, you have alkenes and alkanes. So they do this because they're able to use the smaller chain hydrocarbons are more useful. They can be converted to more useful products, right? Easily. You could make alcohols from this. And with this one, this is like natural gas you could use. So, well, it could be used as fuel. Yeah, fuel. Alright, so with this one, because there's no catalyst and we cracked it, it's known as thermal cracking. So all that was used was a high temperature and a high pressure of about 1,000 degrees Celsius and 70 atmospheres. Now, a hydrocarbon with molecular formula C4H10 is often obtained in the process, as can be seen here. So state two uses of this hydrocarbon. It can be used as fuel and as a refrigerant. So the hydrocarbon in C3 was allowed to react with bromine in the presence of sunlight. Now remember, I told you that alkenes are saturated, so they're basically very unreactive unless in extreme conditions or in the presence of a catalyst. So in this case, the catalyst is sunlight, which provides UV radiation. So it says draw fully displayed structural formula of the monobromo compound form. So I put the bromine on carbon number 1. You could have put it on 2, 3, or 4. Doesn't matter. It's a monobromine. Okay, so they didn't tell us what carbon it would have been on. So this would have been your answer right here. Mono meaning one bromine atom. Monobromo compound. Okay, so state the type of reaction that occurs in C4 between the hydrocarbon and the bromine. It was a substitution reaction simply because there was a hydrogen was substituted for a bromine atom, right? So yeah, there was no, yeah, so that's it. So okay, so propane is another hydrocarbon obtained in one of the fractions during fractional distillation. Write a balanced equation including state symbols for the complete combustion of propane. So complete combustion meaning that it's being burned in air, and whenever you burn alkanes or alcohols in air, well, at this level, that's all we deal with. You can always have a production of carbon dioxide and water coming off. So once you balance these, you want to balance carbon atoms first and then the hydrogen atoms, or either or, but you want to balance those first, and then last you will balance off the oxygen. Now if you get a odd number of oxygens, that is where you would divide that odd number by 2 and put it right in front of the oxygen and multiply the entire equation by 2. But in this case, it didn't have an odd number, meaning that how to put it, like in this case, what means like, okay, so 3 times 2 is 6, and 4 oxygens that give us 10. So we had 10 oxygens on this side, which is not an odd number, right? That's what I mean. So we can simply put a 5 in front of oxygen. So if we didn't get an odd number after we balance the carbon and the hydrogen on the right, if we didn't get an odd number of oxygens on the right, then you're good to go. But however, if you had an odd number like 7 or 3 on the right, then you would have to divide by 2, put the 3 in front here, divide by 2, and multiply by 2. Yeah, I have a video out on that, so maybe I could tag those videos for y'all. Okay, so the 6th and final question. So congratulations, we are almost done. The question is, the ores of aluminum and iron are both oxides. Ores meaning they're like rocks in the soil. Discuss the difference in methods used to extract aluminum and iron from their ores in relation to their positions in the electrochemical series. So I went ahead I wrote out the electrochemical series. It's also known as the reactivity series of the cations, right? And so I put in the carbon this time because of what the question is asking. So these are the markers. Carbon and hydrogen are the markers because these are both nonmetals present in a reactivity series containing metals, right? If you check it out, all of these are metals. Again, please send Charlie's monkeys and zebras in large, high cages more securely guarded. Now, aluminum is right above carbon, while iron is below carbon, just under zinc, next to lead. Now, aluminum is extracted from its ore via electrolysis, and aluminum ore is referred to as bauxite, which is purified to produce aluminum oxide. The aluminum is then removed from the aluminum oxide. The aluminum oxide is white in color, by the way. Iron is extracted from its ore by heating it in a blast furnace. The oxygen is removed from the iron oxide. The oxygen is removed from the iron oxide, leaving iron behind. And so carbon is more reactive than iron, so it is used in the reaction to displace the iron from its ore. So that's why we have it like that. That's why aluminum is removed from its ore via electrolysis, because it's above carbon, right? So carbon cannot displace the aluminum, whereas with iron, the carbon can displace the iron, so we could use carbon to reduce iron. Yeah, that's basically what I wanted to know. But I went on and on because I felt good. And I felt like you needed to know. And a lot of times students tend to pass over the extractions, or no, they don't pass over the extractions. The extractions go over their head because I'll be over your heads because it's just a lot of information. But what I would suggest in the future is that you don't read about this, you watch a video on it. If you want to read about it to make sure the video is accurate, you could do that. And then from then on, you use that video to solidify the information in your brain, because visual representation is everything. From the time you see it in the video, you'll never forget. And you could find many videos on YouTube. Many cartoonized visual videos. Not somebody, even if it was a drawing, you could remember it that way, but they're cartoonized videos. The cartoons that are very cool. Okay, moving on to 2 before I go and talk. Explain which of the methods discussed in A1 will be more suitable for the extraction of a lead ore. Well, first of all, let's look and see where lead is. Lead is right here. Lead is just below carbon, so removal of it from its ore would make sense to follow the method used for removing iron from its ore. And so that's it, because yes, everything that I said is written here. So the method used for removing iron from its ore would be more suitable for removing lead from its ore, because it falls directly on the iron and therefore on the carbon. And then they said write 2 balanced equations that show the process to produce lead from lead to oxide. Now, this goes off of knowledge, and you might have been able to wing this a bit if you had a little bit of information about this, like if you knew something somewhat, but you had to go off of what is done to the iron ore in the blast furnace. First, it is reacted with carbon, solid carbon, to remove the iron and the carbon dioxide, and then it's a 2-step process, right? And then you have carbon monoxide. So actually, it's 2 processes that can be used. So you could have the iron ore also blasted with or reacted with carbon monoxide. So you have one with the iron ore being reacted with just carbon, and then you could have it reacting with carbon monoxide, right? To remove the iron from the ore as well, where carbon dioxide will be produced Okay, and since we know this, well, if the lead ore is subjected to the same treatment, you could react it with carbon, or you could react it with carbon monoxide, and then you just balance accordingly. Here is balance, here is balance. Okay, answer the last question. Oh my God, if you couldn't answer anything here, don't feel bad. Don't feel too bad. Most people wouldn't be able to answer these questions, especially B, because sometimes translation, under pressure translation of information, transference of information while under pressure in exam conditions could make you spaz out a bit. You may have many brain fats in the exam room, so don't feel too bad, because if I was a student doing this exam and this question came up, I would have probably winged it for question 6A. I would have probably known 6A2. I would have known that. And then for this one, if I didn't remember, I would have probably only know this one. Because as a teacher too, I tend to often forget this second part. Because I tend to fumble sometimes, but I tend to forget this second part. So don't feel bad. Once you did well on the other questions, you'll be fine. And trust me, most people in the Caribbean would they'd be experiencing what you're experiencing. And once you put your best foot forward. Alright, so the last question now was more doable in my eyes. It says some metals and their compounds are important to living systems, whereas others could be harmful. True. And consider aluminum, lead, iron, and their compounds. Explain the usefulness of one metal and the harmfulness of one metal in a living system. Again, this question is poorly written, just because I would think they're talking about take one metal and explain its usefulness and its harmfulness. Only one. Pick from the list. Aluminum, lead, or iron. Pick one and explain its usefulness or harmfulness. What they needed to say, because this is how I interpret it, I don't think they were asking me to focus on one metal. I think they wanted me to use two different metals and describe the usefulness or the harmfulness, because then it would, what would make sense is say, explain the usefulness of one metal and the usefulness of another metal to living systems. We use the word another. But to speak like this, of one metal and one metal, use the word another, because then some people would interpret it as just one metal. The word one, first of all, is in caps, and so now I'm thinking they only want me to look at one metal and find the usefulness and harmfulness. So that kind of phrased weirdly, and that could cost you this question. But I think they mean another here. And I chose iron, so iron is present in the blood. It binds oxygen to supply all organs in the body with sufficient oxygen to enable them to function properly. So that's the use there. And then one of them is definitely harmful, which is lead. If it is ingested by children, it can cause brain damage, and if it's ingested in pregnant women, it can cause severe birth defects. Now, lead was discontinued. It used to be used in fuel to remove the knocking, right, so that your engine could run smoothly. But what used to happen was that the lead would be released into the air as a byproduct of this chemical reaction happening in your cars. And so imagine lead in the air and you're inhaling it and all that. Lead was also used in paints at one point. It was also used in makeup. and so it was very poisonous to the human being. And so in paints, what used to happen is that when the paint used to peel on hoses, children get their hands. We were all children, they get their hands on all sorts of things. So start playing with the paint. And what would happen is that they put the paint in their mouth. I mean, children put everything in their mouth: salt, sand, anything. And the paint, because of the presence of the lead, used to have this sweet taste. And so children would continue eating the paint because it's sweet. I mean, mango sweet. You're going to continue eating the mango, right? And so what was found was that children were getting sick. And over time, because of, repeated cases and, the growing repeated cases, they had to stop the use of lead. And so that's it, folks. That's the end of the test. Let me know how you did. And if you don't feel confident, I just remember there's a paper 1. Make sure you go over your paper 1s thoroughly and try your best. I hope that you had a teacher that made sure that you went in with the highest grade possible for your SBAs. And best of luck to you. Best wishes. Put in the work. You have your paper 1 coming up. Don't give up, because your paper 1 could be a saving grace. Okay? All right. Bye, everybody. See you next time around.